Good morning, students. Today, let us see the topic isomorphism of graphs. Okay, so that is when do you say two graphs are isomorphic to each other? Okay, so in order to know this topic, you need to know what do you mean by in degree, out degree, and what is the definition of one function, onto function, and bisective function. Let us see what is the meaning of in degree of a vertex. So in degree means the number of edges directed towards the vertex is called in degree. Number of edges directed towards the vertex is called in degree of the vertex, and out degree means the number of edges directed outwards from the vertex is called out degree. Out degree means the number of edges out to in the outward direction from the vertex is called out degree. And one function. So one function means it can be simply defined as distinct elements in the domain must have distinct images. If distinct elements in the domain have distinct images, then it can be called as one function. Then onto function. Onto function means every element in the codomain must have pre-image in domain. Okay, every element in the codomain must have pre-image in the domain. Then it can be called as onto function. A function that is both one and onto is called bisective function. A function that is both one and onto, that can be called as bisective function. Now let us see the definition of isomorphism of graphs. Okay, so suppose a graph G is given and a graph G dash is also given. So when do you say these two graphs are isomorphic to each other? Okay, there should exist a function f from vertex of G to vertex of G dash satisfying the condition. The function must be bisective function. And the second point is, if there is an edge uv in the first graph, correspondingly f of u, f of v must be an edge in G dash. Okay, so when do you say two graphs are isomorphic to each other? Okay, so the definition is saying that there must be a bisective function between the vertex of first graph to vertex of second graph. Okay, and if there is an edge uv in the first graph, then correspondingly f of u, f of v must be an edge in the second graph. Then the two graphs are said to be isomorphic to each other. Now let us take the example. Let us take the example. So two graphs are given. One graph is having vertices a, b, c. The other graph is having vertices u, v, w. So we need to verify whether these two graphs are isomorphic or not. Okay. So according to the definition, these two graphs will be isomorphic to each other if there is a bisective function from the vertices of first graph to second vertices of second graph, and if uv is an edge in the first graph, then f of u, f of v must be an edge in the second graph. If these conditions are satisfied, then we can say that the two graphs are isomorphic to each other. Okay, so first I need to define the function so that it is a bisective function. Okay, so I have defined the function as I have mapped a to u and b to v and c to w. Okay, so the reason for this is so from a you can have only one edge passing, that is AB, and from U also there is only one edge passing, that is UV. So I have mapped A onto U. The reason is from vertex A there is only one edge AB, and also from U there is only one edge, that is UV. So I have mapped A onto U. Okay, if you want, there is an alternative also. From W there is only one edge, that is WV, so you can map A to W also, but here I have taken A mapped onto U. Okay, B is mapped onto V. The reason is, okay, from B we are having two edges, that is edge BA and edge BC. Okay, and from V also we have two edges, that is VU and VW. Okay, from B we have two edges BA and BC. From V we have two edges VU and VW. So for this reason I have mapped B onto V. So there is no other vertex in the second graph, so that it is having two edges. Now I have mapped C onto W. The reason is C is having there is only one edge with C, that is CB, and also there is only one edge with W, that is WV. So I have mapped C onto W. Okay, so I have mapped A to U, B to V, and C to W. Okay, now we need to check whether this function is bisective or not. Okay, we have already seen the definition of bisective function. So it must be one function and onto function. It must be one function and onto function. Okay, so here, so the vertex of first graph are A, B, C. So A, B, C will be the domain, and vertex of second graph are U, V, W. So U, V, W will be the codomain. Okay, so a function will be one function if different elements of domain have different images in codomain. Okay, so A, B are different and their images f of A and f of B, which are UV, are also different. Similarly, AC are different and their images UW are also different. BC are different and their images f of B and f of C, that is VW, are also different. Since different elements in the domain have different images in the codomain, hence it can be called as a one function. So here the domain is vertex of G, that are ABC, and codomain is vertex of G dash, that are UVW. Okay, next you must verify whether it is onto function or not. Okay, so this function will be onto if every element in the codomain must have preimage. Okay, here, so U is having the preimage A, V is having the preimage B, and W is having the preimage C. Since every element in the codomain is having the preimage, hence it can be called as onto function. Since it is one function and onto function, so it can be taken as a bisective function. Okay, now in order to verify whether the two graphs are isomorphic or not, you need to take an edge in first graph, and you need to see whether correspondingly f of U, f of V is an edge of G dash. Okay, in order to check whether it is isomorphic or not, you need to take an edge UV in the first graph, and you need to verify whether f of U, f of V is an edge in the second graph. Okay, so let us take the edge AB. Let us take the edge AB. Okay, so correspondingly you need to verify f of A, f of B is an edge in the second graph. So f of A means U, f of B means V. So you need to verify UV is an edge in the second graph or not. So clearly UV is an edge in the second graph. Okay, so you take the next possible edge. The next possible edge is BC. Okay, correspondingly you need to verify f of B, f of C is an edge in the second graph. Okay, BC is an edge in the first graph. You need to verify whether f of B, f of C is an edge in the second graph. F of B means V, f of C means W. So clearly VW is an edge in the second graph. Okay, since all the conditions are satisfied, the conditions are f must be a bisective function, it is satisfied, and also the second one, if UV is an edge in the first graph, then f of U, f of B must be an edge in the second graph, that is also satisfied. Hence we can say that the two given graphs are isomorphic to each other. Now let us take another example. Okay, so on the screen you are able to see two graphs. One graph is G with vertices A, B, C, D, E. Okay, on the second graph you are having vertices U, V, W, X, Y. Okay, U, V, W, X, Y. Okay, or YX. These are the two graphs. First graph is denoted by G and second graph is denoted by G dash. Okay, so it is the directed graph. Directions are also shown. Okay, so you need to verify these two graphs are isomorphic graphs or not. Okay, so for that you need to define a function. Okay, so that the function is a bisective function, that is one and onto function. Then you need to check the condition. If UV is an edge in the first graph, correspondingly f of U, f of V must be an edge in the second graph. Okay, if these conditions are satisfied, then we can say that the two graphs are isomorphic to each other. Okay. Now let us see what are the in degree and out degree of each vertex of the first graph. Okay. If you take the first graph G, the in degree of vertex A, in degree of vertex A is 1 and out degree of vertex A is 2. Okay, in degree is 1, the reason is there is only one edge directed towards the vertex A. The out degree is 2, the reason is there are two edges going away from vertex A. Okay, so one edge is directed towards the vertex A, so in degree is 1. Two edges are directed away from vertex A, so out degree is 2. Okay, if you take the vertex B, the in degree is 2 and out degree is 1. The reason is two edges are directed towards B and one edge is directed away from B. Okay, if you take vertex C, the in degree is 1 and out degree is 2. If you take vertex D, then the in degree is 2, out degree is 1. And if you take vertex E, the in degree is 2 and out degree is 2. And if you take the second graph G dash and you take vertex U, the in degree is 2 and out degree is 1. And from vertex V, the in degree is 1, out degree is 2. Okay, so in degree means number of edges directed towards the vertex is called in degree, and the number of edges directed away from the vertex is called out degree. Okay, now we need to define a function so that it is bisect. Okay, so I have defined the function as A mapped onto V, B mapped onto U, C to Y, D to W, E to X. Okay, so here I have mapped the function based on the in degree and out degree. Okay, so let us start with vertex A. So vertex A has in degree 1 and out degree 2. Now let us move on to graph G dash and you identify vertex where it is having 2 out degree and 1 in degree. Okay, so I have mapped, actually in the screen I have mapped A to V. Let us move on to V. Okay, so in V it is also having 1 in degree and 2 out degree. Okay, so I have mapped A onto V. So there can be any other choice. Okay, suppose we have taken, suppose if we have taken any other one, if we have taken U. Okay, the in degree of U is 2 and out degree is 1. Okay, so for A the in degree is 1, out degree is 2. So here I have actually mapped A to V. There can be other choice also, other alternative also, so we are searching for other alternative. So the point is the in degree should be 1, out degree should be 2. Okay, so if you have taken, we already taken, you have take any other vertex. Okay, if you take W, for W in degree is 2, out degree is 1. Okay, we need in degree 1, out degree 2. If you take X, for X the in degree is 2. If you take Y, for Y, okay, for Y the in degree is 1 and out degree is 2. Okay, for Y the in degree is 1 and out degree is 2. Okay, so for A the in degree is 1, out degree is 2. Okay, for V the in degree is 1, out degree is 2. For Y the in degree is 1, out degree is 2. Okay, for Y also the in degree is 1, out degree is 2. Okay, so here I have mapped A onto V. Okay, there is another alternative also, you can map A onto Y also. The reason is for A and Y the in degree and out degree are the same. For A, V and Y the in degree and out degree are the same, so you can map A to Y also, but here I have taken A to V. Okay, then B, I have mapped B onto U. Let us see the reason. So for B, the in degree is 2, out degree is 1. For U, the in degree is 2, out degree is 1. So B and U are having same in degree, out degree. Now let us see. Let us take the vertices C and Y. Okay, for C, the in degree is 1, out degree is 2. For Y, the in degree is 1, out degree is 2. Now take vertex D. For D, in degree is 2, out degree is 1. So D is mapped onto W. For W, in degree is 2, out degree is 1. Okay, for D, in degree is 2, out degree is 1. For W also same in degree and out degree. For E, For E, from the first graph, the in degree is 2, out degree is 2. For X, the in degree is 2, out degree is also 2. So I have mapped A, B, C, D, E onto V, U, Y, W, X based on the in degree and out degree. So there can be another choice also, but I have taken this choice. Okay. Now I need to verify whether this function is a 1 function and onto function. Okay, so A, B, C, D, E are the vertices of the first graph. It can be considered as the domain of the function. V, U, Y, W, X are the vertices of the second function. Okay, that collection can be taken as codomain of the function. So we can see that distinct elements in the domain have distinct images. Okay, AB are distinct, their images. VU are distinct. AE are distinct, their images. VX are distinct. CD are distinct, their images. YW are distinct, and so on. So clearly, you can see different elements in the domain are having different images in the codomain. Hence, it is 1, and you need to verify whether it is onto or not. The elements in the codomain are V, U, Y, W, X. So from the definition of the function, you can see that V is mapped onto A, U is mapped onto B, Y is mapped onto C. Okay. Preimage of V is A, and so on. Preimage of X is E. Since every element in the codomain means vertices of second graph. Every element in the codomain are having pre-images in the domain, hence it is onto function. Since it is both 1 function and onto function, so it is the bisective function. Okay. Now the other condition is, if uv is an edge in the first graph, you need to verify whether f of u and f of v are edges in the second graph. Okay, so I have taken a table. Okay, so there are 3 columns. First one is edge in the first graph, second column is edge in the second graph, corresponding edge in the second graph, and third column is also the same edge. Okay, previously I represented with f, and in the last column I have represented without f. So let us start with edge AB. Okay, so the second point is saying that if uv is an edge in the first graph, then f of u, f of v must be an edge in the second graph. Okay, so I have taken the edge AB. So correspondingly, f of a, f of b must be edge in the second graph. Okay, so f of a means v, f of b means u. So vu must be an edge in the second graph. Okay, from the second graph, you need to check whether vu is an edge in the second graph. Okay, so clearly vu is an edge in the second graph. Now let us move on to the next edge in first graph. AD is an edge in the first graph. Okay, so according to the definition, f of a, f of d must be edge in the second graph. Okay, f of a means, from the definition of function, f of a means v, f of d means w. So vw is an edge in the VW must be an edge in the second graph. Clearly from the second graph, VW is an edge, and so on. Moving on to the last edge, EA. EA is an edge in the first graph. Correspondingly, f of E, f of A must be an edge in the second graph. F of E, f of A must be an edge in the second graph. F of E means X, f of A means V. So XV must be an edge in the second graph. Clearly from the second graph, XV is an edge in the second graph. Okay, since for every edge UV in the first graph, f of U, f of V is an edge in the second graph. So since all the conditions are satisfied, hence we can say that these two directed graphs are isomorphic to each other. Now let us take another example. Okay, there are 2 graphs. First graph is having vertices a, b, c, d, e, f, and second graph is having vertices u, v, w, x, y, z. Okay, we need to verify these 2 graphs are isomorphic to each other or not. Okay, so I have defined the function f as a, b, c, d, e, f. Okay, it is defined as u, y, v, x, w, z based on the in degree and out degree. Let us verify for a and f. For a, the in degree, for a the out degree is 3 and in degree is 0. And what about u? For u the out degree is 2 and in degree is 0. Okay, so based on in degree and out degree, I have mapped the function as a to u, b to y, c to v, d to x, e to w, f to z. So there can be another choice also. Okay, there can be another choice also, you can search for that. Okay, so if you have taken w, For W, the in degree is 0, the out degree is W to X, W to Y, W to Z, the out degree is 3. Okay, so for A, in degree is 0, out degree is 3. For U also, in degree is 0, out degree is 3. For W also, in degree is 0, for W, our degree is 3. For A, U and W, all the three are having same in degree and same out degree. Okay, here I have taken A to U. There is other alternative choice also, that is A can be mapped to W also, but here I have taken A to U. Okay. Similarly, there can be another choice also. Okay, so I have taken the combination like this. So first we have to check whether it is 1 1 function and onto function or not. Okay, so it is to be 1 1. So different elements in the domain must have different images in the codomain. So domain means vertices of the first graph, codomain means vertices of the second graph. So clearly A, B are distinct, their images U, Y are also distinct, E, F are distinct, their images W, Z are also distinct. So you can verify for all the possibilities, hence it is 1 1. Second one you need to verify is onto. Every element in the codomain must have pre-image. Okay, the elements in the codomain means vertices of the second graph, vertices of the second graph. So U is having pre-image A and so on, Z is having pre-image F. So every element in the codomain are having pre-images in the domain, so hence it is bisective function. Now you need to check the last condition. If UV is an edge in the first graph, correspondingly f of U, f of V is an edge in the second graph. Okay, so let us take the first edge AB. So since AB is an edge in the first graph, you need to check whether f of A, f of B is an edge in the second graph or not. So f of A means U, f of B means Y. So you need to verify whether UY is an edge in the second graph or not. So clearly UY is an edge in the second graph. So let us take another edge CD. Correspondingly, f of C, f of D is also an edge in the second graph, must be an edge in the second graph. F of C means V, f of D means X. So Vx must be an edge in the second graph. Clearly, Vx is an edge in the second graph. So you take the last one, EF. Correspondingly, f of E, f of F must be an edge in the second graph. F of E means W, f of F means Z. WZ must be an edge in the second graph. Clearly, WZ is an edge in the second graph. So you need to check all the possibilities. So all the possibilities are shown in the table. Okay, since every edge in the first graph having f of U, f of V as an edge in the second graph, for every edge UV in the first graph, correspondingly f of U, f of V is an edge in the second graph. Since all the conditions are satisfied, hence the two graphs can be called as isomorphic to each other. Now let us take another example. So two graphs are given. First graph is having vertices A, B, C, D, E, F, G, H. Second one is having vertices U, V, W, X, Y, Z, P, Q. Okay, this is an undirected graph. Okay, so in order to verify whether it is isomorphic or not, you need to create a function. You need to develop a function that is 1 1 and onto. Okay, so I have mapped A to X, B to V, and so on. Okay, let us see the reason why A is mapped onto X. Okay, with A you can find three edges, that is AB, AH, and AC. With vertex A you can find three edges from the first graph, that is AB, AH, AC, and also from with respect to X you can find three edges. With respect to X you can find three edges, XW, XY, XU. So that is the reason why I have mapped onto AX. So there is another choice also. If you have taken B, sorry, if you have taken V instead of X, if you have taken V, so V is the vertex V is also having three edges. One is VU, the other one is VP, the other one is VW. Okay, so AXV, all the three are having three edges. Okay, so I have mapped A to X. So there is a other alternative also, that is you can map A to V also. So A is collaborated with three edges, and also V is also collaborated with three edges. So I have mapped A to X. So there is other alternative also, you can map A to V also. Okay, so and finally I have given some combination A to X, B to V, C to U, D to W. Suppose check why E is mapped to Q. Okay, for E it is associated to two edges, EH and EF. For Q, Q is also associated to two edges, QP and QY. So that is the reason why E is mapped onto Q. Okay, and so on. Okay, so I need to verify whether this combination, this function is 1 1 or not. Since different elements in the domain are having different images in the codomain, hence it is 1 1 function, and also different, and also every element in the codomain, that is x, u, v, w, q, z, p, y, are having three images in the domain. Okay, so hence it is onto function. Since it is 1 1 and onto, it can be called as bisective function. The last condition we need to verify is if uv is an edge in the first graph, correspondingly f of u, f of v must be as an edge in the second graph. So I have taken the edge ab, correspondingly f of a and f of b must be edge in the second graph. F of a means x, f of b means v, so xv must be an edge in the second graph. So let us check for the edge xv. From the second graph there is no edge xv. From the second graph there is no edge xv, hence the condition fails. The condition saying that if uv is an edge in the first graph, correspondingly f of u, f of v must be an edge in the second graph. But here ab is the edge, f of a, f of b is the corresponding edge. F of a means x, f of b means v. So there must be an edge xv in the second graph. From the second graph you can see that there is no edge between x and v, hence the condition fails. Since the condition fails, so you can say that the two graphs are not isomorphic to each other. Okay, the point which fails is if uv is an edge in the first graph, then f of u, f of u, f of u, f of v must be an edge in the second graph. This condition fails for the edge ab. Okay, so the important point is you cannot map elements of the domain to same element of the codomain. You cannot map elements of the domain to same element of the codomain. The example is a is mapped onto x. You cannot map some f to x. Here in this example, a is mapped to x, so you cannot map f to x. If that is done, then it cannot be a bisective function. It cannot be a bisective function. But for bisective, it should be 1 1. So if a is mapped onto x, f is also mapped onto x, then 1 1 condition fails. That is, different elements in the domain must have different elements in the different images in the codomain. Okay, so the point you need to remember is while mapping the elements in the domain, you need to check the codomain elements are their images are different. Okay, so in this example the second condition fails. That is, if uv is an edge in the first graph, f of u, f of v must be an edge in the second graph. That condition is failed with this graph. Thank you.